So you've heard a couple of great talks on AADL, architecture. This talk is about how we take systems from architecture all the way down to binary and still preserve the kind of assurance we need. And so the focus of the domain we were interested in is what we call DART, Distributed Adaptive Real-Time Systems. And essentially, when we were proposing this project a couple of years ago, we were looking at what was happening in the industry and in the broader area of autonomous systems. Autonomous systems were just starting to sort of emerge. One particular example we looked at was the Kiva system. So this is what is actually now part of Amazon. But this is essentially the internals of an Amazon warehouse are fully autonomous. So robots move from trucks to the shelves and back, and there's no human beings. And we wanted to see how do we produce these kinds of systems that would actually work in the wild, where we have human beings, where we have uncertain communication, where we have bad localization, etc., etc. So how do we sort of replicate the Amazon warehouse experience in the real world? And that's really what DART was about. And the kinds of challenges we wanted to do in terms of getting assurance were, how do we deal with concurrency? There's this huge state space that we have to deal with. How do we deal with uncertainty? How do we assure both what we call guaranteed properties, things like no collision between the robots, that must never happen, and probabilistic properties, things like on an average the mission should be completed in a certain amount of time given certain resources. And so we quickly realized that neither the testing-based regime that we have right now, nor even verification, formal verification applied kind of in an ad hoc manner here and there would give us the right level of assurance, because none of these verification techniques by themselves tie together nicely into a coherent picture. So that's what we tried to produce, is an engineering process that creates high assurance software for DART systems. And the idea behind this is actually to instantiate two key principles that are actually quite well known. One is compilation. You can take well-defined languages with syntax and semantics and then translate them down to any target architecture. Right? Compilers do this all the time. The other is analysis, which is equally critical, because it's not enough to generate code. You need to have the assurance that that code is going to do what you want it to do. So both these are hallmarks of the DART approach. And so we start with a formal description of the system. We use not only AADL, but a domain-specific language called Dimple that we developed for this project. And they kind of play complementary roles. So AADL gives you the architecture, and you've heard quite a lot of that. Dimple goes one level below and gives you the actual code, the actual protocol, the variables, the statements, etc. that will have. So it's a programming language. Then we do verification, and we end up doing timing analysis to make sure that threads actually have CPU cycles to run. We do model checking, software model checking to make sure that guaranteed properties are always true. And then we do probabilistic model checking, a kind of probabilistic model checking called statistical model checking, actually, based on Monte Carlo simulations to estimate the probabilities of the mission success conditions that we need. Right? And finally, we compile this down to code, C++, and we add in a middleware, we add in the scheduler, etc. And we get the system that we have good assurance will work in practice. So this slide is the DART pie. So I throw this up because it shows you not only the collaborative nature of this project, the fact that 8 or 10 people worked together over 2 years to make this come together nicely, and the kind of tremendous expertise that we needed to make it work out, which we were lucky in some sense to have at the SEI at this point and this time. But also the various disciplines within computer science that we had to bring together, some of which, like architecture, we kind of just pulled off the shelf because we had it already. But the others, like verification and middleware, where we had to make innovations and create new technology, write papers and build tools, etc. So in orange, the orange boxes show you all the various people who kind of took the lead in the various areas of this project. Although it was tremendously collaborative, we worked together and continue to work together. This is a kind of canonical example that I use to motivate the DART problem. So imagine you have a two-dimensional grid, and you have a group of robots that have to move information from one side to the other, right? And they have to go through a high hazard area, which is the top right, it's colored red. You have some mission conditions The one property is that there should not be collisions within the robots. The other property is it should protect the leader to below a certain level of hazard exposure, because if the leader is exposed, then the mission fails. And the final property is you need to finish the mission within a certain amount of time, maybe because you have a limited amount of fuel. So the system can essentially adapt to get between two formations, tight and loose. Right? So the tight formation is on the top right, the loose formation on the top left, and these two formations provide different trade-offs in terms of speed and protection. So the tight formation provides more protection to the central leader, and the loose formation is faster, right? So if you are always in one formation, you're not going to succeed in the mission. If you're in the loose formation, you will be fast, but you will expose the leader to too much danger. If you're in the tight formation, you will protect the leader, but you will run out of fuel. So the key idea here is to actually adapt at runtime to smartly move between the two formations. So essentially move to a tight formation when you need to in the high hazard area, and back to the loose formation when you don't need to. So we'll see what happens with the system later, but the way we develop the system is we start sort of thinking of an architecture. What does the system consist of? Well, it's a distributed system. It has nodes. Nodes play two kinds of roles, either a leader or a protector. And then within the nodes, you have a certain runtime architecture that is baked into by our process. So we think every Dart node has hardware, then a scheduler, then a middleware layer, and then you have various threads doing various things. And these threads are all real-time threads. They have priorities and criticalities and deadlines. And that's really critical to make sure that they can do exactly all the properties that you need. The high critical threads are going to achieve the guaranteed properties like collision avoidance. And as you go down the criticality layer, you're going to move to properties that are more mission specific, that are more probabilistic. Okay, so quick snapshot of the code. So this is actually a fragment of Dimple code for this system. You have what you see here, language constructs that enforce the runtime architecture that I showed on the previous slide. So you have nodes, you have various variables that the nodes communicate with, both within the threads between both threads within the same node and across different nodes. So global variables are shared across all the threads, across all the nodes, etc. And then you have the roles that kind of define what the particular functionality of that node is. And these the functionality is of course implemented in threads. So you see, things like collision avoidance, waypoint, etc. The important thing is that here you see that the leader role has an extra thread that is supposed to do the adaptation. It's supposed to basically at runtime decide when to change formation based on what it thinks is the environment and what is going to happen in the future. So that's the language, is one part of the language. This is the tool chain. So this is one snapshot of our tool chain that takes you from a Dimple program and something we call the mission file. The mission file defines the other parameters of the system. How many nodes are there going to be? How many protectors? How many leaders? What's the runtime time limit on the mission? What are the various probabilistic assumptions that you make? Like if you have inputs from sensors and these are random, what are their distributions, etc., etc. And given all that information, we can actually have a tool chain that takes you from that input down to either a binary or some kind of verification that you can do in the backend. Right? Of course, we need to deploy this on a platform to actually see what's going to happen even if we want to just run a simulation. And so the platform we've been using so far mainly is a simulator called VREP. It's a publicly available simulator that's turned out to be very useful for our project. But we are actually moving more and more toward physical platforms where we can run this the code and see what's happening. So here's a quick video of what would happen for that system. So this shows one run of the system. This is code that has been generated from Dimple and has been then run on the VREP simulator. And so you can see essentially the formation change that you were expecting. So as the system moved into a high hazard area, it went to a tight formation. And then as it's exiting the high hazard area, it goes back to the loose formation. And I want to remind you again that the system is probabilistic. So if you ran the simulation again, you would see slightly different behavior because the underlying hazard levels, etc., are randomized every time. But that's why we have techniques like statistical model checking and Monte Carlo simulations to evaluate probabilities of success. But this is one run of the tool of the system that was generated. We have an alternate tool chain. So the previous tool chain that I showed you is purely command line. It's something it's very easy for us to work with. We've been working on an ADL OSATE based tool chain that basically encapsulates everything that I've showed as an ADL annex. So Julian gave a very nice presentation about how ADL has this annex mechanism. You can take any language and put it inside ADL as a sub-language, and that's exactly what we did. We took Dimple and made it a sub-language. So now you can stay entirely within the ADL ecosystem, and you can drive everything from OSATE. So I do not have time, but please come by. I'll be happy to show you a demonstration of how this works from ADL. But the point is that we are moving more and more toward this kind of ADL OSATE infrastructure so that we can plug into other projects and we can use the host of analysis that is available with ADL. So we actually used a sequence of scenarios through the project to sort of drive our research, and this was important for us to be on track with respect to operational validity and DoD relevance. So we had a team member who had worked with DoD organizations and had the right kind of insights to help us say, here is a sequence of scenarios that would make the outcomes of this project more DoD relevant. And he helped us create this scenarios, and we actually went, and I think we have almost to the last, I think the stage 6 is something we're still working on fine-tuning, but that's mainly an amount of effort, and you need better models to sort of have nodes that can emit radiation and emit threads and so on and so forth. But we actually were quite successful in using the DART tools and the DART techniques to develop all the scenarios. And so I want to show you one of the last scenarios, again a video. So this has essentially a group of nodes that have two kinds of obstacles. You have the green obstacles that are friendly and the red obstacles that are dangerous. And what the nodes are able to do is essentially not only avoid colliding with each other, but also detect those obstacles, and based on what level of threat is perceived, take different actions. So you see that when the node gets to a red obstacle, it actually moves much higher up because that's what it's programmed to do. It's programmed to be as far away from these hostile obstacles as possible. So that's another scenario that we did. And again, this is one video, but in practice, what we do is we program this and we run it and we see what happens. Okay, so now I'm going to, in the next 4 or 5 minutes, quickly go through the technical areas that we worked on. And I'm going to use the banner on top to sort of indicate which area we are talking about. So if you are not sure, just look on top, and the area that's highlighted is the area that we are talking about here. So this is self-adaptation. So this is about how do we sense the system, sense the environment, and basically make an intelligent decision about our action, our tactic that we should perform to achieve some mission goal. And the way this is set up is actually about like a game. It's a two-player game between you, the system, and the environment, which is an uncertain adversary. And the idea is to basically at each point of time when we want to make a decision to just unfold the game tree to a level that you can within the given amount of resources that you have, and then use some kind of strategy synthesis algorithm to find the best strategy within that finite look-ahead horizon, right? So it's something like what a chess program might do, for example. And so the work that was done had two phases. One was to use a tool called Prism to synthesize strategies. This is a probabilistic model checker. And the more recent work that was done in year 2 of the project was to replace Prism with a stochastic dynamic programming algorithm that essentially does the same thing that Prism does, but much, much faster, 10x faster. And on the left you see are the two papers that give you the technical details of this work. The top one is about the Prism work, the one on the bottom is about the stochastic dynamic programming. So now we are switching to statistical model checking. So this is you're given a random system and you're given some predicate, something that must that either holds or not at the end of a particular run of the system. And the system is probabilistic, so on some runs it will hold and some runs it will fail. What you're interested in is to compute the probability of it holding. So map it to your favorite mission. And what statistical model checking does is a technology that actually was invented in CMU, but we were given funding by Dr. Beno a couple of years ago to start looking into it. And since then, what we've done is basically taken this into a more mature area where you can apply it on bigger and more complex systems like Dart systems. So we actually encode the property that we're interested in inside Dimple in a very formal way. So you see at the bottom, you see an expect statement. That's essentially the property. And then we use a bunch of simulations, Monte Carlo simulations, to get to an estimate of the probability with a desired precision, which is expressed, which is exposed in something called a relative error, or RE. So we want to know what the probability of the mission success is within 0.001, for example. And so technically what happens is you have a master that's coordinating all the Monte Carlo simulations, and the master basically runs a whole bunch, and it can actually do this in parallel. So if you have a lot of supercomputers or high performance computing infrastructure, you can run lots of simulations in parallel, and then collects the results, computes the probabilities, computes the precision that you have, and if you have reached the desired level of precision, you just stop, and if not, you keep going and you do more simulations. So that's at a high level what happens. And in practice, what we have implemented is a tool called Demeter that actually does all this simulations by isolating them in Docker containers. So there's a fair amount of engineering that has happened to make this work for complex systems. And till date, so this is online. It's within the SCI. It's backed up by, I think, 10 blade servers that can run hundreds of simulations in parallel. Till date, I think we've run over like 3-4 million simulations, and the best thing is it's very robust. We found that we can literally start the experiment and go to sleep, and when we get up in the morning, we see the results. So that's very good from our points of view. And we have a couple of papers at RV last year and again this year that describe the details of this project. What were we able to do? The one quick part about this actually is something called input attribution. So, in statistical model checking, traditionally all you get is probability. What you don't get is why the probability is what it is. And that's really important because that's like the counter example. So if your probability came to be too high or too low, what you would like to do is, how can I improve the system so that the probability goes down or up as I desire? And for that, you need kind of a cause-effect analysis. And so what we have done is implemented a technique based on machine learning, logistic regression, that can actually take the results of all the simulations and learn from that the most probable causes of that contribute to the probability being high or low. And that's been very successful. That's actually the second, the RV16 paper talks about in detail how we call it input attribution. This is one area that we are actually trying to apply this technique outside the SEI. So we partnered up with NREC, the National Robotics Engineering Center. And what we are trying to do is use statistical model checking to evaluate the quality of a planner that they have. So they have a system where they can give a robot a high-level command, like go to the front of that building or go to the left side of this building. And the robot then takes that and does a sequence of steps starting from speech synthesis to sort of planning, and then all the way down to actuation, like low-level path planning and actuation, and actually tries to make that follow that path. And what they see in practice is they run it, out of 10 times it runs, it fails 2 times and doesn't perform so well the next 5 times, etc. So the whole thing is kind of ad hoc, subjective, and it's based on a human expert. And it's also very hard to do it. Like, if you're working with real robots, running 10 experiments often takes quite a bit of time. So when they saw our statistical model checking work, they said, hey, can we use simulations like you do to actually evaluate the quality of the planner? And that's what we've been trying to do. And we've had some encouraging preliminary results, but I think we need to push this a little further to see how far we can go with statistical model checking in this. But I think most of it is just sort of engineering issues and figuring out how to put a right robot model inside a simulation, etc., etc. Okay. So real quickly on scheduling. So this is work that we've been doing. So we build on a prior work on something called zero slack rate monotonic scheduling. And this is about, like I said, threads in Dart have both criticality and priority, and they may not be compatible. So you could have high criticality threads that have low priority, etc. And we need to manage these two when the resources are limited. And that's what ZSRM does. It provides a guarantee that in overload conditions, high criticality threads are always going to get preferential treatment. In normal operating conditions, it's going to be basic rate monotonic scheduling. And what we've done on top of this is something called ZSRM DAG scheduling, which is think of how to schedule systems where a logical task may not be happening on one node, but maybe actually spread over multiple nodes of the system, and how do we do scheduling for these kinds of scenarios. So I want to quickly finish up with the functional verification, the model checking part of the work. And this was about trying to use model checking to prove things like no collision. And again, the approach here was to encode the property in dimple in a very rigorous way, and then use a process called sequentialization that takes you from a distributed program to a sequential program, and then use off-the-shelf model checkers, software model checkers, to verify those programs. And essentially, we did this in 3 stages. We did initially something called bounded model checking that helps us prove correctness of protocols up to a finite number of steps. Then we did unbounded model checking, which was to prove it for unbounded number of steps, but for a finite number of nodes. And then finally, we did something called parameterized verification, where we were able to show that the particular collision avoidance protocol we have will actually work no matter how many nodes you have in the system and how large of a grid you have. And this was the final result we got along that direction. And the other piece we did was, okay, so analyzing software only gives you guarantees that are independent of the underlying controller. So if you really want to avoid prove collision avoidance, you need to reason somehow about the physical platform and the way the controller is actually moving the platform, the robot. And so we teamed up with a researcher from Air Force Research Lab, Stanley Buck, and we kind of combined software model checking with hybrid reachability, which Stanley is an expert in. And we were able to show that in a very compositional way, we can reason about a collision avoidance protocol working in conjunction with an actual controller algorithm on a platform, and prove that it will give you real physical collision avoidance. So that was a powerful result. And the paper on the left shows you, has more details about this approach. So this is the last slide. So we have other FY16 work. The first, actually I'm going to talk about that next. It's about verifying real-time schedulers. And then the future work, which is just started, is how do we do runtime assurance. So this is an idea that, as systems get more complex, you are not going to be able to formally verify the whole thing. In fact, if you have a very complex machine learning component that's doing some very smart algorithms, you want it to be unpredictable in some sense, because otherwise it's too restricted. What you don't want it to do is something terribly bad, right? And so if you can define what the terribly bad means, and if you can put a guardian, a monitor, in the system that is non-circumventable, then you kind of get the best of both worlds. You have a very powerful system that will almost always give you very high capability, but the guardian stops it from doing something really bad. So that's I think is a really interesting line of work that we are just starting in another 2-year project.